So we talk about Newton's laws of motion, but sometimes we forget about like the history of it. So in science, sometimes people have really good ideas. Sometimes scientific discoveries are just accidents, but usually somebody has a general idea. Aristotle was one of the first people on record that started talking about motion. He was around 350 BC, and I don't know if you would call him a scientist as much as he was a philosopher. So in the early days, around 300, 400 BC, there were a lot of philosophers, and they thought about stuff, right? Philosophy literally means the love of thinking, people who love to think. And so they would just think and think and think, and they would try to come up with ideas, which is almost like the precursor to the scientific method, right? So Aristotle was watching stuff move, and he realized like something causes stuff to move, right? So his idea was a force is needed for constant motion, but really what he should have said was acceleration. So go ahead and write down acceleration real quick. Now, acceleration and force have a mathematical relationship. Force is equal to the mass times the acceleration. The more mass of an object there is, the more force is required to cause it to accelerate. You can have motion in the absence of acceleration. So I think what we're talking about here is when something is sitting still, how do I force it to move? Now, they had wheels back then, and so they probably had carts that could be pulled by horses and stuff like that. So a cart would just sit there all day long until a horse pulled it. So that would be a force, right? We said a force is a push or a pull. Okay. And basically, we measure how that change in position, which ultimately is a velocity, and then we measure the change in velocity as acceleration. Okay. Now, Galileo came along. Now, Galileo really tried to be a scientist. He was a little more scientific in his methods. And around 1600, he experimented with rolling balls down wooden ramps, right? So Newton was the first person, although I don't know, he's pretty close to a contemporary of Galileo, but Galileo was fascinated with things rolling down wooden ramps. Okay. Galileo is responsible for a lot of things, actually. Galileo got in trouble too. He was placed on house arrest because he disagreed with the church. He said that the Earth was round and it orbited the sun. And he didn't get in trouble for being a scientist or having scientific discoveries or anything like that. He was in trouble because he was yelling at the officials. So back then, the church was kind of like the government. And so he was basically arguing with the government, saying they were wrong. And they were saying, well, we're going to reserve judgment. And anyways, to keep him quiet, they put him on house arrest. But he still went and spoke different places. He was an interesting guy. He would go to parties and stuff, and he would do tricks, but they weren't really tricks. They were just things that happened naturally based on physics. What hits the ground first, a heavy ball or a feather sort of thing, stuff like that. Pulling out a tablecloth underneath the candlesticks. We now understand it as physics, but these were little parlor tricks that he did that were based on motion and physics and stuff. He also invented like one of the first telescopes. He was fascinated with celestial bodies, which is a fancy word for planets and stars and stuff. So this is an example of the type of ramp or a ramp that you could study, right? So you could roll a ball down a ramp. You could roll a ball down this ramp. Now, the ringing bells basically give you an audio signal as to when the ball is in a certain location. Okay? So, for example, this little bell here will ring when the ball goes past it. So, one of the observations, even if you didn't have like a fancy stopwatch, because they didn't have fancy stopwatches, they certainly didn't have iPhones, they certainly didn't have video recorders where you could go back and look and see what the exact time is. But what they observed is the ringing of the bells would get closer and closer together, right? So if these bells were the same distance apart all the way down the ramp, and you rolled down the ramp, the bell would go ding, 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 and the ringing of the bells would get closer and closer together as you got further down the ramp, because the speed of the ball would increase. So that increase in velocity was acceleration. And this was fascinating to people at the time, because they're like, whoa, I never really, because not many people just watch stuff roll down hills, right? Roll down an inclined plane. And this is a very structured inclined plane. It has a very specific angle. So this is, and due to gravity, it would have a constant acceleration. It should fall down the same amount every time. You could even place the bells in different locations if you needed to, and have different notes, and you could make it play a song if you wanted to. So those were some of the things that they did. There's some other examples. You could roll the ball down this ramp, and then it would switch over. Now, Galileo also studied, and you should write this down, studied how gravity produces a constant acceleration. So just by observing the behavior of things rolling down, and we knew that to some degree gravity, by the way, we still don't know how gravity works. We could just measure what it does, right? I don't know what makes stuff fall down towards the center of the earth. We have this idea, we call it gravity. We have a bunch of equations that we can use to figure out how much time it takes for it to fall down to the earth. There are some theories right now about gravity particles and stuff like that, but we really don't know how it works. But what we do know is that it causes things to accelerate at a constant acceleration. And at about sea level on Earth, it's 9.8 meters per second. Anyways, Galileo said that moving objects not subjected to friction or any other force would continue to move forever. Now, this came from watching through the telescope, watching planets and stars, right? You could even watch the moon with your naked, like you don't need a telescope. Has anybody looked at the moon through a telescope though? It's really cool. When you look at it through just a regular telescope, you can see the craters on the moon. And if you watch it for a long time, you could see the moon, like it takes a really long time, but you could kind of see the moon move and stuff. So it's kind of neat. And if you watch it a couple nights in a row, that's even cooler. But it basically, it's like a little, I don't want to say it's a planet. It's not a planet, but it's a little, we would call it a celestial body. It's something, it's a big ball out there in space. But one thing it does is it has a consistent motion. It has a constant motion. It's measurable. It's predictable. Okay. I shouldn't say constant because it varies from time to time. If you get into the little details of things, everything has an impact on it. So through his telescope and watching things like the moon and the different stars, you could actually see Venus. You guys probably don't know that. Maybe we'll go. Maybe I'll pull up a thing on my computer to show you guys that you could actually see Venus at night. It looks like a star, but it's actually Venus. Certain times of the year. This time of the year is a good time to see it. Okay. Then Newton comes along, and this is towards the end of the Galileo phase of science. And Newton built on the work of Galileo and other people too, and he published his results in a book called, the translation of this is The Principles of Mathematics. So in this book, he kind of lays out like how to study motion, but also lays the foundation for calculus. Okay, there's a lot of arguments. Some people credit Newton for developing calculus, but then some people would say that Leibniz did it. They're two different people, two different parts of the world. Not that far apart though. But Newton first had to define mass and force. And basically what Newton discovered was if something was bigger, you had to push harder. But once you got that thing going, for example, if you roll a big ball down a ramp, it doesn't speed up as fast for some reason, but then it kind of does. Right? Takes a little bit more to get it going. I mentioned to you guys when we played that video of the NASA facility where they drop the bowling ball and the feathers in a vacuum. It falls pretty far. I can't remember what it was. It was like 30 meters or something. I can't remember the exact height. But they're basically falling at the same time. Okay? And we were talking about the velocity. And the assumption is that because the bowling ball is bigger, it's going to go faster. The truth is, it goes the same speed as the feathers, right? But what happens when they crash into the little box of sand? Well, the feathers just kind of bounce off the sand. That bowling ball makes a big crater in the sand. Why? Because there's more force. So the acceleration is the same for both, which means that the velocities increase the same over time. But because it's more massive, it wants to keep going. That bowling ball has more mass, which means it's going to have a greater impact or a greater force. That's why we float down towards the center of the earth. If I jump up in the air, I'll fall down. Why? Because the earth is much more massive than I am. Technically, the earth I have a gravity because I have a mass, and I attract the earth to me, but the earth is way more massive. If two of us were out in space, and we just sat out in space for a long enough time, eventually we'd start to float towards each other. We'd have an acceleration towards each other. Okay?
I'd have more acceleration than he would have.
That's funny. All right. So then Newton's first law of motion was that an object does not change as long as the motion of the object does not change as long as the force acting on the object is zero. So if we go out in space and we shoot our little Nerf guns like this, and I'm out in space and I shoot it, nothing is acting upon it. There's no gravity from Earth pulling it down. It'll float off forever. That's why when you watch one of those space movies, and every once in a while in the space movie, somebody has to go out and do a spacewalk, and to save everybody's life, they float away. They have no way to get back. Okay? They have no way to get back. But they'll float on forever. That's why when you see space movies or astronauts and they go outside in space, they're always tethered, tied up to the object. Okay? Whoops. Did you guys get that written down? Now, we say that a little different. We say that an object in motion remains in motion in a straight line, and an object at rest remains at rest. But we're basically saying that unless a force acts on something which causes an acceleration, it'll keep doing what it's doing. And this goes all the way back to Aristotle. He noticed that that wagon would not move unless a horse pulled it or people pushed it. Right? Galileo was a little more sophisticated, had some bells and ramps, but Newton actually did the math and used calculus to get very precise measurements. Okay. Can we go on to the next one? So one thing that there's this concept of inertia, and inertia is the tendency of an object to resist change in motion. The more massive an object is, the more inertia it has. Okay? Objects want to keep doing whatever it is they're doing. Oh, lost one. Nope, not one. So if I push the school bus, when the school buses come here, I can't push the school bus by myself, but all of us got behind the school bus and pushed it, right? All of us got behind the school bus and pushed it. Once that bus was going, it would probably have a tendency to keep going. Has anybody ever pushed a car before? Yeah. When you push a car off the side of the road, when you push a car off the side of the road, once you get it going, it's not that hard to keep it going. You really just have to overcome the friction. That's inertia. Okay? Remember when we did the tug of war thing? How do you win a tug of war? Does anybody remember that? You just have to be first. In theory, when you do a big tug of war with a bunch of people, usually the groups are pretty evenly matched. So the first team that can get the motion going in their direction will usually win, because the net force, somebody's pulling this way, somebody's pulling this way, they're usually pretty close to a net zero. But if this team can get the motion going this way first, they're more likely to win. So the key to winning tug of war is not being stronger, bigger. The key to winning a tug of war is to be first, the first team to pull. That's it. And then once that motion gets going, the only thing you have to do is maintain your force. Okay? Because that motion that you start will want to keep going in that direction. So if you could get that other team quickly to move a little bit, they're going to be fighting against it the whole time. Let me zoom in on this. Now, you don't need to write this down, but this is a satellite in space. It's called Pioneer 10. And basically, this was a probe that was sent to Jupiter. Jupiter is 200,000 kilometers away. The launch date was pretty close to my birthday, March 2nd, 1972. It flew by Jupiter in 1973, so it took it a whole year to get there. Okay. The mass of this object was 258 kilograms. So at NASA, what they do is they just kind of calculate the path that it needs to take, when to launch it, how to get it to where it needs to be. But there's very little fuel needed, because once that thing gets out in space, if they can avoid the other planets, it'll basically just kind of keep going. There's a Tesla car in space. I can't remember the exact numbers, but SpaceX launched like a Tesla Roadster or something in space, and it's just going towards the Mars. But I can't remember the speed. It's like crazy fast, because if you continue to accelerate a little bit in space, it just keeps speeding up. Once you turn that acceleration off, that velocity stays the same. And we know that to be true here on Earth, right? What's the velocity in the x direction? Well, once we get it going, it stays the same. That's how we're able to predict where the little darts go, right? Okay. This is on some of these probes that we send out. This is interesting. We sometimes think about we're wondering, by the way, once it sailed past Jupiter, we just let this bad boy go, okay? So in there's this plate that's kind of saying, hey, we're human beings. This is a man, this is a woman. And this is some information that we try to make it like symbolic. So if somebody discovers this probe, they'll go, oh, this was made by these people. And, you know, it gives us some information. If we're saying that this is our star, we're the third planet from the star, right? Earth, yes. Did you fill it out? Yeah. Okay. You don't have to write this down, but it's kind of fun. Let me zoom in on this. So now what is the mathematical relationship that Newton developed that's going to help us with that? Okay, write that down. So the second law of motion is that force is equal to the mass times the acceleration. Okay? Force is equal to the mass times the acceleration. So the more mass of an object is, the more force is required to cause it to accelerate. Now, if you want to find acceleration, you just take that equation and do a little bit of algebra, and you get that the acceleration of an object is the amount of force applied divided by the mass of the object. So the acceleration is inversely proportional to the mass. The bigger the mass, the less it accelerates. Yes.
Reminds me of the Doom Turtle.
Yeah. What's that?
The Doom Turtle. It was a tank the United States military made during World War II to cross the Siegfried line.
Yeah.
And it weighed 90 tons. But they put the same motor in it that the Sherman tanks had.
Yeah.
So you're trying to get a 500 horsepower motor to move 90 tons. So of course the first one burst into flame and burned itself.
Yeah.
Because the little motor couldn't do it.
Yeah.
Its mass was far too much for its force.
Yeah. I'm surprised they didn't engineer that out first.
They did. They started in 42. They abandoned it in 45 when somebody figured out, hey, you can take a bulldozer and you just cover up the Siegfried line with dirt, and we can just drive over it.
Yeah. So one of the things you can talk about force is actually, you could actually measure force in horsepower, but your engine basically creates a force, right? It's kind of it's really fascinating how a car engine works. That's why when they want cars to go really fast, they make them lighter, right? You guys know that. Now most of our cars are made out of plastic, but if somebody wanted like a high performance car, they want it to be lighter because it's easier to make it go fast. Okay? If you want a fast car. So that would increase the acceleration. I have a thing I'll do at the end of the notes about shopping carts. All right, so write this down. Your force is equal to the mass times the acceleration, but if you guys ever done these triangles before for formulas? So if I want to find the mass of an object, if I want to find the mass of the object, I just take the force and divide it by the acceleration. If I want to find the acceleration of the object, I take the force and divide it by the mass. If I want to find the force, I multiply the acceleration times the mass. Okay, that's the mathematical relationship. Now the units for force is newtons, right? This is newtons. The units for mass is kilograms, and the units for acceleration is meters per second squared. So a newton technically is kilogram meters per second squared. Okay. we'll do an example of this in a second. Can I scroll down, or you guys need a minute? Yes.
What is one Newton?
It's 1 kilogram meter. So force is, so 1 Newton is 1 kilogram meter per second squared.
How much energy that would put out?
So the energy, you would just divide the, so you'd have to convert it to work, and work is just force per time, I think, if I remember off the top of my head. So, yeah, work is, or it could be over a distance. Actually, I gotta remember off the top of my head. I think it's actually over a distance, and then the energy is the work over time. So that's a mathematics. So it all builds on the other one. So your work would be, let me see, I could be wrong, but it could be, I think it's kilogram meters squared over seconds squared. And so that would be work. And then energy would be kilogram meters squared seconds cubed. So you're measuring, yeah, I think that's right. I think that's right off the top of my head, if I remember correctly. Because work is the amount of force that's applied over a distance. And so we measure distance in meters in science and physics. And then work done over time is energy. Right? So then, and we usually measure that in seconds. Now, you can convert it to hours and all that stuff. But, yeah, that's a good question. Well, when we're finished with this, we'll explore that. So here's an example. I want you to write the example down. You have 6 newtons of force. We'll get a 3 kilogram car, which, by the way, is a very small car, to accelerate 2 meters per second. That's like a car, like a toy car, something like this. Okay, something like that. Now, if I want to find the mass of the object, and you'll see that the math works out every time. If I want to find the mass of the object, I just take the force. So generally in your homework, you're going to be given 2 of these 3, okay? And so if you're given the force and the acceleration, you can find the mass by taking the force. In other words, if you have 6 newtons and 2 meters per second, if you take 6 and divide it by 2, that will give you the mass, which is 3, okay? And then if you wanted to find the acceleration, you just take the force and divide it by the mass. And the math works out. I'd write it down, but my smart notebook hasn't been so smart lately. And it has a tendency to screw up. And so this is basically the relationship. So I have an engine that applies 6 newtons of force. You don't have to write this out. It's just a picture you can look at to see. On a car, that car weighs, let me zoom out so you can see the artwork on this. That car weighs 3 kilograms, and it accelerates at 2 meters per second. And so this is the chart of how that all works out. Okay. Actually, if you want to, I see some of you are writing it down, so I'll leave it up for a second. All right, can we go to the next slide? that's basically, I like this way of remembering it. Or you could write out all three of those equations. It doesn't really matter. I just write this one out and then just plug the numbers in and solve for whatever I need to solve for. Okay. Here's another way you could do it. If you're given 6 newtons, you could plug it into here. You don't have to write all this down. Remember, I do want you to write this down. You guys should know this off the top of your head, but all free-falling objects are accelerating at 9.8 meters per second towards the center of the Earth at sea level. As we get further away from the center of the Earth, it's a little less. Not that much. It's a little less. So a satellite in space that's in orbit around the Earth, at some point in time, if they don't have rockets that keep it in orbit, it will fall back to the Earth. We had that happen. Remember that? What was that? Satellite that fell, like in the 80s, and everybody was freaking out, and it didn't hurt anybody, but.
I remember Skylab fell.
Yeah, I think that was it. Wasn't it in the 80s, or was that the late 70s? Yeah, they were freaking out for a minute. So anyways, it doesn't accelerate at 9.8 out in space because you're further away from the center of the Earth. So there is this, the gravity between two objects is the distance between the two centers of the mass. The greater that distance between the two centers of the mass, the less of a acceleration or force. Okay. I think we're just about done. Here's another example. I do want you to write this down. So no matter what they give us, if they give me 30 newtons and the acceleration of 3 meters per second, then I know the mass is 10 kilograms. If they give me 30 newtons and the mass is 10 kilograms, I can figure out that the acceleration is 3 meters per second squared. And if they give me the mass and the acceleration, I can figure out it'll take 30 newtons for me to cause that object to move. Oh, formula, right? This says work, but really work is you got to do that over distance. And this is the answer, the number, and these are the units. So in other words, the force is newtons. The unit for mass is kilograms. And then the unit for acceleration, I think this is meters per second squared, but it's a squiggly. I would just write the circle down. Okay. So this is another way to think about the units. So we're going to have a lot of equations that we use, and then sometimes they use the same letters, and sometimes I could take numbers and multiply them and add them and subtract them all day long. I won't know for sure if I've done it correctly unless I do what we call dimensional analysis. I gotta make sure that if I'm doing newtons, that somehow there's a mass in there, and there's a length, and there's a time per time, or seconds squared. If I don't have those dimensions in there, then the number doesn't represent what I need it to represent with regards to force. In other words, if you don't, sometimes this is a common mistake students will make. They'll say an object starts at rest and then in 3 seconds speeds up to 20 meters per second. Spell it out? Okay. An object speeds up to 20 meters per second in 2 seconds and has a mass of 1,000 kilograms. What is the force that that object will pull at? Well, kids will plug in the velocity of 20 meters per second. Well, that's not what the formula calls for. You'd have to go back and calculate what the acceleration is, which is 10 meters per second. And then that would be the acceleration that you'll plug in. So that's where we're going with that. Okay. when we start to do the homework on that, it'll make more sense, but. All right, we're almost done with the notes. I don't know why that's in there. Yeah, I think we're done with the notes. Any questions?